Hello everyone, welcome back to Native Engineering. Today we are doing an exercise on shock load. The exercise that we are doing reads as follows. A weight of 20 newtons falls through a height of 50 millimeters onto a collar at the end of a 20 millimeter diameter shaft. The length of the shaft is 1.2 meters. And then they gave us the Young modulus as 200 gigapascal. And then the questions, they say, calculate the force in the rod, that is number 1, and number 2, which is 6.2, they say, the instantaneous strain energy stored in the rod. Number 3, the total instantaneous extension. Number 4, the instantaneous stress in the rod. Number 5, the final extension. So this is the diagram that we are given, and they gave us the length. This is the length of 1.2 in meters. They gave us the diameter of 20 millimeters. The weight is 20 newtons. This is the Young's modulus, the height of that it will fall before it hits the collar. And yeah, this is the diagram that we're given. So from here, I'm going to erase the diagram and we're going to attempt the questions. Question number 1. They say, calculate the force in the rod. Remember, we have this formula. W H plus X is equals to half X total change in length, which will be the potential energy is equals to the strain energy. And then from here, we are going to consider what X is equals to. We know X is equals to the force times the length divided by area, Young modulus of elasticity. We're going to put it here and here, which will give us W H plus, we put this, which will be F L divided by area, Young's modulus, close bracket. It's equals to half the force F L divided by area E. W H plus X F L divided by area, Young's modulus. Let's make this one thing. It will be something like this. Force squared times length 2 area E. Let's divide both sides by W. Divide both sides. This W will cancel with this W, and we are going to have W here. Erase this. We are going to end up with an equation like this. We are going to substitute. Remember, we have everything except for the F that we are looking for. So I'm going to delete this and move this upward. From here, we are going to substitute. What is the value of H? The value of H is 0.05 plus F we don't have, that's what we're looking for, times the length we're given as 1.2 divided by the area. We're given the diameter, therefore we're going to say times 0.02. We're given the diameter as 20 times the Young's modulus, which will be 200 times 10 to the power 9, and that's equals to the force. This is what we are looking for, squared times the length, which is 1.2. 2 times pi divided by 0. Pi divided by 4. pi divided by 4 times 0.02 squared times our Young's modulus, which will be 200 times 10 to the power 9 times our weight, which will be 20 newtons. Here is 0.05, and this will give us a positive 6 times 10, which will be equals to, this will give us, it should be 4.775 times 10 to the power negative 10 times f squared. Therefore, we are going to equate to 0, where we will end up with something, an equation like this: 4.775 times 10 to the power negative 10 f squared minus 6 times 10 to the power negative 8 f minus 0.05, which will equate to what? To 0. And then from there, we are going to use the quadratic formula to solve this equation, to solve for the value of f, which is the force that we are looking for. So let's take this up. Quadratic formula. Divided by 2a plus or minus divided by to the square root of b squared minus 4ac. And then from here we are going to substitute. Negative, what's our p? This is our p. It's negative 6 times 10 to the power negative 8. We are going to use the positive root. To the square root of negative 6 times 10 to the power negative 8 squared minus 4 times a. What is our a? Our a is 4.775 times 10 to the power negative 10 times c, which is negative 0.05. Let's extend this and this. Divided by 2 times a, which is 4.775 times 10 to the power negative 10. And then this will give us the value of f as 10.296 kilonewtons. And that is our value of f. And then we go on to question number 2. They say calculate the instantaneous strain energy stored in the rod. I'm going to erase this. That will be 6.2. What is the formula to calculate strain? Strain is given by half fxt. This we calculated, and we know that x is equals to f l a e, which will be squared l 2a e. And then we are going to substitute our value for f. We got that it is 10.296 times 10 to the power 3. That's a kilo. And don't forget this square. Times our length, which is 1.2. Then it's 2 here. Times our area, which is 0. It's 4 here, right? Can I keep on making 0? 0.02, which is the diameter of the rod, times Young's modulus, which is 200, times 10 to the power 9. And this will give us our strain energy as 1.012 joules. And then we go to the next question, which is question number 3. They say the total instantaneous extension. So let's erase this. Three 6.3. We are going to use the formula to calculate strain again. Half Fxt. We now have strain, we have force. The only unknown that we don't have will be the xt that we are looking for. So we make it the subject of the formula, and we end up with what? U times 2 divided by F, something like this. And then we got that our strain energy is what? Let's say 2 times our strain energy, which is 1.012, times our force, which is 10.296 times 10 to the power of 3. And then that gave me 0.197 times 10 to the power -4, which is our total strain, our total instantaneous extension. And then we go to the next question, which is question number 4. They say the instantaneous stress in the rod. That will be 6.4. Instantaneous stress, we know stress is given by force divided by area. Our force we already calculated, times 10 to the power of 3, divided by our area, which we know, pi divided by 4, times the diameter, which is 0.02 squared. And this will give us a stress of 332.773 megapascal. Final extension, we know they are talking about the extension which is affected by the gradually applied load. Therefore, it will be given by the weight times the length divided by the area times the Young's modulus of elasticity. And our weight, we know that it's what? We're given as 20 Newton, times the length is 1.2, divided by the area with a diameter of 0.02, times modulus of elasticity, which is 200 times 10 to the power 9, which will be a gig. And then this will give us 3.82 times 10 to the power 7. Always make sure that your final extension is lower than your instantaneous extension. And that's how we wrap this question. I will see you on the next one.